In this part, we'll be looking at what are dislocations in BCC and what are the stacking sequence in case of BCC. So let's look at the BCC crystal structure. So we have a BCC crystal structure where you have atoms at the corners and one atom at the body center, that is at half position. And let's mark the slip systems in case of BCC. Let's write it down. So we have 110 type of planes which acts as a slip planes and 111 type of direction which acts as a slip direction. And let's mark this slip system on this crystal. Let's do that. So let's mark the slip plane first. So you have this kind of planes. These are 110 type of planes which acts as a slip plane, and the slip direction will be along body diagonal, which is here. This is the slip direction. Now here I have marked this slip planes, two consecutive slip planes, that is 110 type of planes. So let's say that this is a type of plane and this is a B type of plane. So these are all 110 type of planes. In this B layer, the atoms will be sitting over atoms in the A layer, where the positions of B layer will be in between this kind of A atoms. So let's see this stacking in more detail. So let's consider these are the atoms. The red color atoms are in the A layer and green color atoms are in the B layer. And what are the positions of these B layer atoms? So they will occupy positions above. Let's mark those positions. So B layer atoms will occupy this kind of position. So the B layer atoms will sit on these positions. And now what will be the A layer atoms will be? So A layer atoms will sit on this kind of positions. And thus this makes an AB-AB stacking. So when I talk about a BCC structure and when I talk about 110 type of planes, what kind of stacking we have? We have AB-AB kind of stacking. And thus this stacking makes a BCC structure. Now what is the slip direction? Let us mark that slip direction on this schematic here. So you have a slip direction along this way. So let's mark that also. So this will be your slip direction. And let's have a glide of these atoms in a B layer or a B layer over a layer. So let's do that and see how it happens. So when there is a glide of B atoms over A atoms along this 111 direction, that is by a Burgess vector. So we have moved by a Burgess vector of A by 2, 111, and when I move that, it returns the crystal structure. So you can see that there will be no stacking fault or a fault which has been created when I moved by this Burgess vector. And the stabilized positions for B atoms will be these locations, because these are the locations of minimum energy. So you have positions of B atoms in this at these positions, and you have positions for A atoms which are at these locations, that is in between two B atoms. And thus we have AB-AB stacking which remains same even we have glide of B atoms over A atoms. Now let's consider a scenario where I move these atoms or B atoms over an A atom. What will happen? It will have AA kind of or layers or BB kind of layers. So let's say I would like to create a stacking fault in this kind of 110 planes in BCC. What can I do is that you have, let me write it down. So you have AB kind of stacking in 110 planes. So if I want to create a stacking fault, I will remove this layer or I will remove this layer. And thus if I remove B layer, what will happen? We have B kind of stacking. Or if I remove A layer, what will happen? We have this kind of stacking. And thus this kind of stacking brings BB stacking over each other or AA stacking over each other, and thus this will be a high energy configurations. And thus when I say 110 planes, it will have very high stacking fault energy when I try to create any fault in the layers, and this remains unstable. So in principle, there will not be any stacking faults which are formed on 110 type of planes in BCC. Now let's look at some other stacking of planes in BCC, and let's look at the stacking of 112 type of planes in BCC. Now this is a BCC structure. So what I have done here, there are two unit cells of BCC. So this is one unit cell and this is another unit cell. So there are two unit cells, one above each other, and let's mark atoms. So you have A atom here, and let's mark this 112 planes. And which are these 112 type of planes? Let us mark that. So we have this kind of 112 planes, and let's mark atoms in this kind of 112 planes by, let's say here B in one kind of 112 plane, and then you have another kind of 112 plane that is here, which is on which the atoms are marked as C. Then we have another kind of 112 plane which is on which the atoms are marked as D. Let us mark here one more time. So we have this D layer which I am marking here. These are 112 type of planes, and we have similarly for E atoms which are marked on this 112 type of planes, then F atoms which are marked on this 112 type of planes. Let's mark F atom here once more to understand it clearly. So we have this kind of 112 type of planes which are stacked above each other, which makes this BCC structure. And you have how many layers of this 112? You have 6 layers of 112, which makes complete BCC. So you have A, B, C, D, E, F. So we have this stacking sequence of 112 planes, which makes a BCC structure. Now let's understand this stacking sequence in more detail. Before going into that, we know that this 112 also is one of the slip planes. So if you revise and see, so you can see that we have already mentioned that 112 is one of the slip planes in BCC, and these are this 112 type of planes. Now let's look at the trace of this 1 bar 12 on 110. What do I mean by trace? So let us mark that 110 plane. So you have this 110 plane which I am marking over here, and so these are 110 type of planes, and these are 110 type of planes. And what do I mean by trace? So trace means the projections of atoms on 112 type of planes on 110. So here you can see that I am projecting all the atoms on 112 type of planes on 110 plane. So let's look at this, and this is a trace of this 1 bar 12 planes on 110. So here you have C atom, we have C atom. Here you have A atom, here you have A atom. And now you see, now you are projecting. Let's mark that. So when I am projecting here, when I am projecting this B atom at this plane, that is 110 plane, I can get this position. So when I am projecting B atoms here, I will get this position here. And similarly, you project all the atoms and you get this kind of stacking. So I'll remove this, and you can say that when I'm projecting this atoms on 110 plane, we'll get this kind of structure. Now let's look at this stacking in more detail. So you have this bar 110 direction which is marked here, you have 001 direction which is marked here, and you have 1 bar 12 direction which is marked here. Now this direction is perpendicular to this plane. So what are these planes? These planes, these all will be, let us write it down. So these all will be 1 bar 1 2 planes, because this is a cubic system. So if I know the direction, I can find out what is a plane, because this direction will be perpendicular to these planes. Now let's mark these distances. So we know that this B is a projection on this 110 plane. Let us do that here again in this diagram. So this will be our 110 plane. Let me mark it here again. And we have said that this is a projection or trace. So this will be a position for or projection of this B atom on this plane. So this distance we are showing. So this is a distance we are showing over here, and that is A by 2 bar 110. And you can see from A to C here along 001 direction, A to C here, that will be our A001 distance. Now this is a projection of B atom. Let us mark that also. So let's say here also B atom will come, because this is a 112 plane which is marking this B atoms here. So you have this B atom here, and this B atom is marked over here because this is a trace of 1 bar 12 on 110, and this distance will be clearly A by 2 001, because A to C is a distance having a magnitude A001. So this will be half of it, and it will be A by 2 00. Now what will be this distance? So this is nothing but our Burgess vector. So let's write it that down. So this will be our Burgess vector, which is B, and it will be given as A by 2 bar 1 1 1. So you just have to add these two and you get this vector, which is B Burgess vector A by 2 bar 1 1 1. Similarly, all this C to C or D to D, E to E, F to F will be Burgess vector. Now let's mark some planes over here. So I have drawn some planes which are in this way, and you know that this will be 111 type of planes, because this is bar 11 direction and these planes are perpendicular to it. So these planes are 111 type planes. Let us write that down. So these are 111 type planes, and you can say that what will be the distance between these two consecutive 111 type planes. So you know that this is from E to E is a Burgess vector. So this is divided into three parts. So this will, the distance between these two consecutive planes will be B by 3. So this D I am talking about. So this D will be B by 3 and its magnitude will be A by 6 111. So here in this case, let us correct it there. So it will be here A by 6 bar 111. So this D is a magnitude. Magnitude of this D will be always B by 3 and it should be A by 6 111. And so this is what the distance between these two consecutive 111 plane will be. Now if you look at these lines or planes, you can say that the positions of B and E resembles, positions of D and A resembles with each other, positions of F and C resembles with each other. So these planes or the arrangement of these planes will play a role when we talk about a stacking fault in case of BCC. Now let's move ahead, and we have seen the stacking of this A, B, C, D, E, F in this fashion. And now let's consider this plane and let us mark this position of, so this will be representing a 111 type of plane. Let us mark that because this is perpendicular to this direction. And let's have this displacement because we are talking about two consecutive 111 type of plane, and let's So let me write it down, let me clarify it. So you have this direction to be 112 type of direction, and thus these planes these planes will be all these planes will be 112 type of planes, because this direction is 112, so this direction is 112, so these planes will be 112 type of planes, and we have a glide on this 112 type of planes along this direction. So let's do that. So when I move it in this direction, what I see is that these atoms will fall over each other, and these are just above each other. So this configuration or the energy configurations will be very high. So these are falling over each other, and let's move it by another a by 6 111 magnitude, and you can see again it falls on this layer, and thus the energy configurations will be very high. And let's move by another a by 6 111. So you have this configuration which reaches over here, and this regains this a position. So we have moved by how many times? We have moved by 3 times. Let's write it down. So we have 3 times movement by a magnitude of this. So this becomes a by 2. So this is nothing but our Burgess vector, and thus when I move by a by 6 bar 111 direction, you create energy configurations which are unstable, or which are high energy configurations, and thus we can say that one atomic layer of stacking fault is not possible in case of BCC when I'm talking about 112 type of planes. So we have 112 type of planes, and glide occurs along 111 directions. Now let's look at this scenario in more detail. So we have seen that one atomic layer stacking fault is not possible because you have high energy configurations, and when we move completely, like let's say from this point to this point only, it retains the structure, and that is by a Burgess vector. Now let's look at this in more detail. So we have arranged these atoms in this way. So we have seen this the trace of this 112 type of planes on 110 planes, and why we have done this? Because we want this direction, that is 111 directions, to be horizontal, and as I have mentioned you earlier, so this direction is 112 direction, so these planes will be 112 planes. Let us write it down again. So we have this direction which is 11 bar 111 1 bar 12 direction, and thus these planes will be 1 bar 12 kind of planes, and this direction, so this direction will be bar 1 type of direction. And let us mark these planes. So these planes will be kind of 111 type of planes, because this direction is 11, so this will be kind of planes, because this direction is bar 11 direction and these planes are perpendicular to it. Now what we do is that rather than gliding one layer, we glide all the layers above it on the bottom layer. Let's do that. So we glide it by a by 6 bar 111, and let's do that. So when it glides, you can say that when I glide it by a by 6 bar 11 all the layers, so you can say there will be a configuration which has a lower energy. There is a fault which has been created. Now you can see that this layer can be considered as D layer because it is falling on D. So let us write it down. So this will be a D layer. Now F has converted to D layer, and A will be converted to So this is an A layer. So we can say that A will be converted to B layer here. So you can have a B layer, and so this will be converted to B layer. So we create a stacking fault in this kind of gliding when we glide all the layers, all the top layers on the bottom crystal. So let us write it down. Initially what we had, let us write it down. Initially we had A, B, C, D, E and F. Now what after gliding, what has happened is you have A layer, B layer, C layer, you have D layer intact, E layer has become C layer, F layer has become D layer. So we have a stacking fault which has been created over here. So you can see there is a stacking fault here which has been created, and thus unlike when we moved only one atomic layer, this stacking fault will be stable. And so we had stacking, or after slip, this will be the positions of atoms, and this stacking remains stable. So stacking fault due to consecutive glide on 112 plane. So this were the consecutive planes, and we glide it by A by 6 bar 111 magnitude, and this remains stable. So in 112 type of planes, you can get a stacking fault. So let us write it down before we wind it up. So we had 110 type of planes, and which has AB stacking, and there cannot be any stacking faults. Stacking faults cannot be possible. Then you have 112 type of planes. We have stacking of A, B, C, D, E, F, and here stacking fault is possible, but not for one atomic layer. And other stacking faults which is possible by consecutive glide of 112 planes, and this is possible. And in both the cases, what we have is that, what is the slip direction in both the cases? It will be 111 type direction. And we'll be looking at the consequences of this when we discuss about twinning in the material or twinning in BCC materials. So with this, I will stop here.